Welcome to module number 45. Recall that we started covering compressed sensing. The main idea is that sparse signals can be processed, acquired with a reduced number of measurements. And we covered briefly the compressed sensing encoder and then the compressed sensing decoder. What we're going to do in this module, we're going to go into more detail about the compressed sensing encoder. We're going to begin with image acquisition and discuss two other related applications. And later on in the next module, we'll be talking about the decoder side, the signal reconstruction side. So here's an illustration of how you can use compressed sensing to perform image acquisition. This is a single pixel camera, a concept for compressed sensing measurements that we worked on in around 2006. So just, you can think about a projector. You've, in classrooms, not during the pandemic, but in the past, you've seen projectors in classrooms. And the idea there is that you have an image, and that image is being formed by a pattern on an array of micromirrors. And that array of micromirrors, you have light from a very powerful bulb that's shining off the micromirrors, and with a bunch of lenses is going toward a scene. Now, what we're doing here is dual to that, a bit different, but also similar, that we're taking light from an outside scene. After passing it through a lens, it's the focal point is at the array of micromirrors, meaning that each element, each micromirror, is going to correspond to 1 pixel in our scene. And we're either going to accumulate optical energy from that pixel and send it toward our photodetector or not. And the way how we'll do that, we'll either have the mirror reflecting the light toward the photodetector or reflecting it away. So this way, you have one arrangement of the micromirrors, and that'll give us at the photodiode a summation of optical energy only for the pixels whose corresponding mirrors are pointing toward the photodiode. And that way you'll have one compressed sensing measurement, and then you're going to modify your the orientations of the mirrors, and you're going to take another linear combination of pixels, and that will give you another measurement, and you'll continue. You'll have many orientations, perhaps thousands of orientations of the mirrors. Each of them will give you another measurement. And these compressed sensing measurements are being performed directly in the analog domain because we're controlling through the micromirrors what photons are being accumulated at the photodiode. And we only need a single photodiode. So whereas normally you would need to scan, let's say, 100,000 or even 1,000,000 pixels, with this approach, you only need to modify the pattern of the mirrors some number of times, which is typically going to be perhaps 10 times less than the number of pixels, meaning that the overall image acquisition time is lower than before. So here are initial results from 2006. We looked at a 64 by 64 image, 4,096 pixels of the letter R. And if you use 400 wavelet terms to approximate that letter, you get a somewhat blurry version of the letter R. And we then took our compressed sensing camera and we looked at an image of the letter R. But because things were not perfectly aligned and so on, the image on the DMD array was also quite blurry, quite noisy. And using 1,600 random measurements, recall 1,600 is approximately 38% of the 4,096 pixels. We ran a compressed sensing algorithm, and we got this outcome, which overall it's somewhat blurry, it's somewhat noisy, but it definitely looks like an R. So this was in 2006, where the number of measurements was 38% of the number of pixels. And a modern image reconstruction approach, here we had a paper from 2015. The number of pixels had increased to 128 by 128. That's approximately 16,500 pixels. And we used 5,000 measurements, which is now approximately 30%, a somewhat lower measurement rate. We used an iterative approximate message passing, or AMP algorithm. We're going to look into some details of that algorithm a few modules from now. And overall, this is a typical quality of an image reconstructed from 5,000 measurements. So from image acquisition to hyperspectral image acquisition, and in particular, we're going to be discussing hyperspectral images acquired using a CASI scheme that I'll soon describe. So a hyperspectral image, normally in standard cameras, we think about three colors, red, green, and blue, and we have three color planes, and the information at three different types of sensors is fused together. Now in hyperspectral images, you have dozens or even hundreds of different colors, and here we have different wavelengths from 452 nanometers, 461 up to 659. And at each of the frequencies, it's a different color. And for each of the color, I'm showing you the corresponding image. And these are called image slices. And we have different image slices at different wavelengths. These image slices can be stacked into a three-dimensional cube. And you can imagine that, for example, each of these images may be 256 by 256, and you may have several dozen of these images. But there are, as you can see, adjacent colors are going to be similar images, similar image slices. Applications of hyperspectral imaging include medical imaging, where you're trying to evaluate different types of materials in a patient, geology, astronomy, and also remote sensing. Now, the way how we're acquiring this, as I briefly mentioned earlier, is using a scheme called CASI, or Coded Aperture Snapshot Spectral Imaging. The idea is that you encode the hyperspectral cube with a mask, and you pass your hyperspectral image through a prism, and the prism creates a dispersion effect. The dispersion effect, it has the property that different frequencies, different colors are moved spatially to a different extent. Therefore, on a 2D focal plane, we're going to have stacked versions of different image slices. And each image slice, for some reason, my laptop keeps skipping slides and stuff like that. I'm trying to correct for that. We have a superposition of different image slices, but some of them are shifted, translated more than others. And the algorithm is aware of that, and the algorithm uses that information to attempt to reconstruct the entire hyperspectral cube. So we mapped CASI to a linear system meaning that we're approximating it by a matrix multiplied by vector form. The vector form here corresponds to the hyperspectral image cube. And we used another approximate message passing based reconstruction algorithm. And this is an iterative scheme. Here you're seeing the original image only shown for a visualization purpose with the RGB, three different colors. And after 400 iterations, we got a fairly clean outcome. If you look at some of the details, for example, the face of this Lego piece to the right, you'll see a bit of fudginess, but overall good quality. And more importantly, the color slices were aligned well. That brings me to our third application, deblurring in radio astronomy. The National Radio Astronomy Observatory, or NRAO, operates a bunch of large radio telescopes in West Virginia. Their largest radio telescope, here's a picture of it, is the surface is a parabola where the focal point is way over the parabola in the air. The parabola is pretty large. I've been there and I've actually been at the focal point. The parabola is 105 meters wide. So you can imagine basically a football field of these moving elements, and they move because the parabola is suffering from wind and it's rotating and so on. So you need to constantly align the surfaces to achieve a very nice parabola surface. And overall, the radio waves are being focused at the sensor, and we want improved imaging from this device. So overall, the big picture of things is that the parabola is pointing toward a certain direction at the sky. We're then focusing the radio waves at our sensor. And based on these different directions that we're looking at, we're going to get an image signal, and we want to reconstruct that. Now, part of the problem is that the incoming image is being convolved by a point spread function. The sensor has a point spread function, meaning that if you're looking at a specific angle, you're not going to get information exactly at that angle. There's going to be a 2D convolution. And so we have the image, we're performing a 2D convolution with this point spread function, and then there's noise. There's a lot of noise because we get a tiny amount, a minute amount of energy from the radio telescope, whereas we're getting a lot of energy from man-made interference and other problems, including the weather. And we want from these measurements to recover the image. And part of the challenge is computational. For a problem that has on the order of 100,000 pixels, typically the number of measurements is going to be in the tens of millions. So here's an illustration of a preliminary result. This is an image of the Orion constellation. We were incapable of storing the corresponding measurement matrix on our server. Again, it would have, this type of matrix would have perhaps tens of millions of rows and tens or hundreds of thousands of columns. So this would be unrealistic to store it. And instead of that, we constructed the matrix on the fly by calculating it on our server. We could do that because the point spread function gives us a specific structure. Because of basically all this computation, again, the size of the matrix is had on the order of 10 to the 12 elements, the image reconstruction took a week, and possible future work could look into subtracting interference in order to reduce some of the artifacts in this image. So again, this module looked at hardware schemes that can capture signals in a compressive way, and the next module is going to look at the reconstruction.